Hello, everyone. Welcome to the Analog Electronic Technology course. In this lesson, we will continue learning the analysis methods of bipolar junction transistor amplifier circuits. In engineering analysis, we usually begin by using estimation method or graphical method to perform DC analysis of the amplifier circuit. Then, we build the small signal model of the bipolar junction transistor to estimate key performance indicators of the amplifier circuit. Since the bipolar junction transistor is a nonlinear device, analyzing amplifier circuits becomes quite complex. When a signal is sufficiently small, the bipolar junction transistor's characteristic curve near the quiescent operating point can be approximated by a straight line. This allows us to use the small signal model to analyze and calculate parameters such as voltage gain AU, input resistance Ri, and output resistance Ro. The small signal model of the bipolar junction transistor is shown in the figure. When the input signal is small, the input characteristics near the quiescent operating point can be approximately linearized within a small range. The base emitter junction, B to E, can be modeled as a linear resistance RBE. For small power transistors, it can be approximated using the following formula. Among them, RBB prime is the volume resistance of the base material, typically between 100 to 300 ohms, and RBE prime is the resistance of the emitter junction. The output resistance RC is very large and can usually be neglected. In the linear operating region, the output characteristic curves are a set of equally spaced parallel lines. The current amplification factor beta of a transistor is a constant. In the active region, the collector current IC is controlled solely by the base current IB, independent of the collector emitter voltage Vs. This reflects the fact that the input current of the bipolar junction transistor controls the output current. Based on this, the C and E terminals of the bipolar junction transistor can be modeled as a current source controlled by beta times IB. Note that the direction of the current source cannot be assumed arbitrarily. It must be determined by the actual direction of IB. For low-frequency models, the effective junction capacitance can be neglected. This gives us the small signal equivalent model of the bipolar junction transistor, also known as the H-parameter equivalent model. Using the small signal model, the dynamic performance analysis of a basic common emitter amplifier circuit generally involves the following steps. Draw the DC path, calculate the Q point and the AC parameter, RBE. Draw the AC path of the amplifier circuit. Draw the small signal equivalent circuit. Use the small signal equivalent circuit to estimate the voltage gain, input resistance, and output resistance. The drawing sequence of the small signal equivalent circuit is shown in the figure, from the original schematic to the AC path, and then to the small signal equivalent circuit. According to the definition of voltage gain, AU equals VO over VI. In the diagram, the direction of IC and the output voltage VO is opposite. So VO equals negative IC times RC in parallel with RL. Note the negative sign here. In the input loop, VI equals IB times RBE. Since IC equals beta times IB, substituting this into the expression allows us to eliminate the intermediate variable IB. Therefore, the voltage gain AV equals negative beta times RL over RBE. The typical calculated value is around 100, indicating that the common emitter configuration has strong voltage amplification capability and is commonly used in intermediate stages of integrated circuits. Here, it is recommended that you memorize the voltage gain formula for direct application in the future. The larger the input resistance of the circuit, the more energy it can obtain from the signal source. Therefore, voltage amplifier circuits with voltage sources as signal sources prefer higher input resistance. In the basic common emitter configuration, the input resistance is the parallel combination of RB and RBE. Since RB is usually much larger than RBE, Ri is almost equal to RBE. Obviously, this is a relatively low input resistance and does not meet the ideal condition. The output resistance reflects the stability of the voltage gain of the amplifier circuit. The smaller it is, the more stable the gain, and the stronger the load driving capability. The output resistance of a basic common emitter amplifier, calculated using the test voltage method, is RC. Comparing the voltage gain expressions of the common emitter circuit under loaded and unloaded conditions shows a nearly twofold difference, indicating that the voltage gain is not very stable and the load driving capability is weak. The reason lies in the relatively large output resistance. When the signal source has internal resistance, what is the relationship between the voltage gain AU and the source voltage gain AUS? Mathematical analysis shows that AUS and AU are related through a specific expression. Since the common emitter input resistance is small, it results in significant energy loss. As a result, there is a large difference between AUS and AU. Finally, let's summarize the applicable conditions for the small signal model analysis method. When the input signal amplitude of the amplifier circuit is small, the bipolar junction transistor operates in the linear region of its volt-ampere characteristic curve, i.e., the active region. The H parameter values are determined based on the quiescent operating point. Therefore, the dynamic performance of the amplifier circuit is closely related to the magnitude and stability of the quiescent operating point parameters. The main advantage of the small signal equivalent circuit analysis method is that it makes it easy to calculate dynamic performance parameters of the amplifier circuit, such as AU, RI, and RO, and it is also suitable for higher frequency analysis. However, a key limitation is that in both the bipolar junction transistor and the amplifier circuit's small signal equivalent models, voltages, currents, and H parameters refer to incremental, AC, quantities and cannot be used to analyze or calculate the quiescent operating point. Based on the performance indicators above, please think about the following. Is the common emitter amplifier circuit an ideal circuit module? What other shortcomings does the circuit have? Alright, that concludes this lesson. Thank you, goodbye.